And good evening, wherever you are. Welcome to this keynote session for the Wireless Power Week. My name is Don Tian. So I was I'm the one of the original creators, so to speak, with the Wireless Power Week. Started with Professor K. Wu in 2018. So I'm so glad to see this event. It's growing so fast. So today we have the great pleasure to have Dr. Morris Kelsler, who is the Chief Technical Officer from WPTC, to give us a talk titled Wireless Charging for Electrical Vehicle Moving to the Mainstream. So Morris is actually, as we say, is the CTO of WPTC, and he is in charge of the research and the development technology within the company. He also, before that, he worked at Virginia Tech Georgia Tech, with Research Institute, where he actually led many efforts in technology development and basic research. So with a great pleasure, and I welcome Dr. Morris Kelsler. You have the floor.
Thank you.
I should stop here. So Morris, you can present your screen.
Okay. Now. Can everyone see that?
Yes.
Great. Well, thank you for the opportunity to speak today to everyone attending this conference. It is exciting how much attention the technology is getting now, and all the people that are interested in it and involved. So today I'm going to talk about wireless charging for electric vehicles. You know, technology has a history of going wireless, from corded to cordless, starting with phones in the 90s, going from your landline to your mobile phone, also with data in the next decade, going from wired LAN to wireless and Wi-Fi. And we feel that power is the next wireless revolution, going from conductive charging to wireless charging. It's no secret that electrification of transportation is underway, and there's an acceleration in the number of electric vehicles that are in the market today and are projected to come in the future. This chart just shows the three largest markets for electric vehicles right now, and how they've grown over the past years and how they're expected to grow. And part of that is that's gotten the attention of the automakers, and more of them are putting their emphasis on deploying and offering electric vehicles. So there's much more choice for consumers these days. And last year, over 100 brands offered electric vehicles to the market. Now we've got to charge all of these vehicles, and currently the way to do that is by plugging in. Now that has some inherent weaknesses that go with it. It can be difficult to handle the cords. They can be dirty in public places, out in the open, can be demanding, and it can be difficult depending on how the things that are going on around and the things you might be doing. So there is a better way to do this, and that's through the use of wireless charging, where it offers a complete worry-free experience for the user. All you need to do is park your car, get out, and it starts charging automatically. And there's no compromise in the speed at which you're able to charge. Level 2 charging at 11 kilowatts, that can be done, and the technology scales up to hundreds of kilowatts for wireless charging of heavier duty vehicles. And when autonomy comes, this is really the only option for offering full autonomy to vehicles in the future. And the interest in the technology has certainly been growing. This conference is an example of that. Here, I just did a quick search of the papers in the IEEE papers over the past decade or so. And you can see that the number of publications there have been has just been growing. There's been a lot of interest in the research that technology has advanced and has matured to the point where it's ready to be deployed. Another key development in wireless charging is the establishment of standards for EV charging. In the US, that was SAE with their J2954 standard, which was issued last October after a decade of work by 100 individuals and from automakers and suppliers worldwide. There was also a parallel document issued for the communications for these systems, allowing systems to interop with each other and systems from different vehicle makers and suppliers to be able to talk to each other. Now, on the global stage, ISO and IEC have also been working on standards over the same time period, and they've started to issue their standards, which are largely compatible with and harmonized with the J2954 standard, establishing sort of a global commonality for systems so that they can be developed and operated worldwide. China started a little bit later on their standards development activity, but they have moved very quickly. And last year they issued a part of their standard, a portion of it, with the remaining part to be issued this year. Now, this standard is not exactly the same as the others, but it's largely compatible, and it's possible to build systems that will be compatible across markets. So the standards are ready. And as you look to the future for autonomous vehicles or other levels of autonomy, then wireless charging is really the only way to go for being able to provide charging in those cases. For example, auto parking technology allows your car, once you get out, it can go park itself and it can charge while you're taking care of your business, whatever you may be doing, shopping or otherwise, and be ready to go when you are ready to go. Other autonomous vehicles shown here are also prime candidates for wireless charging, and it offers a way to charge these vehicles where you can't do it plugging in. So the time is right for EV wireless charging. The technology is ready, the standards are there, the interest in the vehicles is there, and so it's ready to be deployed as we move forward. First in sort of static situations, parking, but moving towards semi-dynamic and dynamic situations and heavier duty charging as well. So what goes into one of these systems? Many of you might be familiar, if you're attending this conference, you know sort of what's in a wireless charging system. But for this application, there are really three main components that are in the system. There's some electronics in a wall box that we call it, that attaches to the grid, that basically takes the grid power at 50 or 60 hertz and converts it to the high frequency that's used for charging. In this case, 85 kilohertz frequency band is really what's been standardized. There's a component that sits on the ground, could be in the ground, called the ground assembly, that houses the coil and other sensor systems, and this is where the field is created. And another unit that sits on the car that captures that field. and some power electronics to convert that to a signal, DC signal that can be used to charge the battery. There's a communications link between the two sides, and in this case, it's really a Wi-Fi 802.11 standard that's been adopted for this use case. If you look a little bit one level down into what's actually in a system, you can show a block diagram really of the components. And this really represents many sort of wireless charging systems using magnetic resonance. Starting on the left, there's a grid connection with a power factor correction. It basically converts from AC to DC, then followed by an inverter to convert back up to the 85 kilohertz signal. There's an impedance matching block coupling the energy to the resonator, which is creating the field. On the vehicle side, similar looking structure with a coil and resonator, an impedance matching network, and then some power electronics to convert that 85 kilohertz back to DC in order to charge the battery. And then the controllers on each side to control both the power flow and the system operation. Now, what are the challenges in building a system for this application? The use case demands that the system operate over a wide range of conditions. For example, various partitions where the ground side and the vehicle side are not well aligned, different ground clearance heights of vehicles, different types of vehicles. And the end result of this is the magnetic coupling between the ground coil and the vehicle coil varies over quite a range, about 2.5 to 1 in a typical situation. And this means that the impedance seen by the ground side could vary by a factor of more than 6, putting some demands on the ground side electronics that they'd be able to cover that. In addition, the battery voltage that you're driving varies over a range during the charge cycle of potentially 1.5, that's sort of 1.5 to 1, that's sort of a typical range. And so that provides a varying load impedance on the system, which also is seen by the ground side. So in the end, if you don't do anything, then the ground side's got to cover about a factor of 10 in reflected impedance. Another challenge is the impact of the vehicle and on the ground side. And you find that the inductance of the GA coil can vary quite a bit depending on the ground clearance of the vehicle, the parking offset, and 20% is not uncommon when looking at vehicles ranging from sports car to SUV. The variation on the vehicle side is really due to the presence of the ferrite on the ground side, and its variation is considerably less, but it also is an impact on system operation. And finally, if for an interoperable system, in other words, a ground side that's supposed to operate with different types of vehicles, then that puts some additional challenges on what the ground side needs to be able to do during operation. So how do you address some of these challenges? Well, one approach is to add some tunability to the secondary side to reduce sort of the burden on the ground side electronics and improve efficiency. For example, you can have a tunable impedance or tunable reactance in your impedance matching on the vehicle side, which helps control the VA resonator coil current and helps improve efficiency. You can have an active rectifier or perhaps a power stage after a DC to DC converter after the rectifier to help take some of the battery voltage variation out on the system. You can have dynamic tuning on the ground side to help reduce the requirements on the inverter. In other words, the voltage and current range that it needs to support to help not only reduce the cost, but also improve the efficiency of the ground side electronics. And you need this flexibility when you're trying to operate with different vehicle types, potentially vehicles that, you know, are made different ways in terms of the electronics and things on the secondary side. And it's possible to do this. This is just a plot of an efficiency, a histogram of measurements taken over the full range of ground clearances from 100 millimeters up to 150 millimeters. Over full range of offsets, a full range of battery voltages, and you can see that the efficiency is quite good. This is from all the way from the grid to the battery, ranging from 89 to 93 with an average of over 91. So it's possible to build a very efficient system to cover this use case. But the powertrain is not really sufficient if you're building a product. So there's some additional subsystems that are required to operate safely. These include foreign object detection system, a metallic object that gets onto the GA surface can heat up, so you need to be able to detect that and stop system operation in that case. Or if somebody happened to crawl under the car and reach into the power transfer field, you need to be able to detect that. And you need ways to verify that the system is really in a proper position to allow charging. In addition, there are regulatory constraints on any product. You've got to meet the local EMC guidelines for emissions, as well as human exposure. And last but not least, in order to achieve broad deployment, you have to get to the cost to the point where it's a system like this can go on the broadest range of vehicles. So let's look at some of these subsystems. Foreign object detection, or FOD, or FOD, as I might call it, is designed to detect metallic objects that might be on the GA surface. And these objects can heat up. Some examples are shown here, from thin metallic foils, paperback foils, to paper clips. And so your FOD system has to be able to detect these during the power transfer to protect against potentially hazardous conditions. Now, how small of an object do you need to detect? Well, that's a function of the surface B field that's on the surface of the GA. And for a typical field at 11 kilowatts of around peak field of around 3 millitesla, then you need to be able to detect a standard size paperclip. And because these objects are not really absorbing that much power, it doesn't take that much power to heat up a paperclip, then just doing power or efficiency measurements and trying to track lost power like is done at some low frequency or lower power systems is not sufficient for these cases. And there are several possible approaches for a system like this. Inductive sensors, thermal sensors, camera-based, etc. The second area that must be considered are the human safety guidelines. So these are put out by several groups. One of them is the International Commission on Non-Ionizing Radiation Protection, or ICNIRP as I call it. They've put out guidelines for human safety exposure to 85 kilohertz fields. And they've defined it in terms of what they call basic restrictions, and that's the electric field that would be induced inside the human body if exposed to that field. That's a difficult thing to measure. Actually, there's no way to measure it right now, sort of in situ at these frequency levels. So they've also defined a reference level that if the external field is less than that reference level, 27 microtesla, in this case at 85 kilohertz, then you're assured of meeting the basic restrictions. However, you can be above this reference level and still meet the basic restrictions because of the conservative nature of that reference level. There are also implanted medical devices, or CIED here, that place some limits on the stray fields that around the charging system. In this case, the limits set are around 15 microtesla at 85 kilohertz to eliminate any chance of any interaction with those implanted devices. So for a vehicle charging situation, the areas around the vehicle and inside the vehicle where there might be people that are unaware of this charging, and just the general public that might be there, you're expected to meet these human exposure and CIED exposure limits at all times. Underneath the vehicle, the fields are going to be higher there, and it's certainly less accessible. So underneath the vehicle, you need a system to detect if somebody were to get into a region where the basic restrictions would be exceeded. So we call this a living object detection system, which needs to operate in portions of region 1 underneath the vehicle. So how do you determine what that system needs to do? First, if you look at the fields underneath the vehicle, and this is just showing a simulated result of the fields produced by a pair of coils here, the ground coil and the vehicle coil, sort of in a worst case position and maximum ground clearance, maximum offset, and just showing the magnetic fields around the system underneath the vehicle. And you see that one side is slightly higher than the other. So, and that field exceeds the reference levels. So then we have used this to evaluate against the basic restrictions here in order to determine the extent over which this LOD system needs to operate. And you do that by using, again, EM simulations of a human phantom or other sort of canonical objects. Here we just show an example of a hand phantom that's been placed close to the ground coil in between, in the region of the highest field, to evaluate really how close can you come before you would exceed those limits. And in this case, you reach the limits when the hand is just about 7 centimeters from the edge of the ferrite. So your LOD system, your requirements for your LOD system are based on doing this type of evaluation for other potential body parts that might be in that region. So this is sort of the range. You can see that it doesn't have to operate over the full underside of the car, but really only needs to operate in the region right around the ground coil.
And Morris, you have a couple of minutes left, so just give
Okay,
a heads up. Yes.
Thank you for the time check. So the last thing I wanted to touch on is the EMC requirements. Certainly any product that you want to put into the market has to meet the local EMC requirements. And in the US and in other regions, the WPT system, at least the power transfer portion, is considered what's known as a ISM device, industrial, scientific, and medical device. So in the US, that means the system has to meet FCC Part 18 limits. Other regions have their own requirements. In the EU, it's currently under debate how you characterize this system, whether it should be ISM or a radio device. And Witricity is leading efforts globally to try to establish the reasonable limits for these systems to enable broad deployment. These pictures just show how the measurements are done. Below 30 megahertz, we're measuring, it's a measurement of the magnetic field using a loop antenna. The picture below is a picture from a test site at TEK RF Solutions, showing a vehicle that's being charged and the antenna measurement about 10 meters away. Now, what do these limits look like? In the US, Part 18, FCC Part 18 is defines what the limit is, but limit has been defined at 300 meters. So it's a certain field level, electric field level in this case, at 300 meters. However, it's difficult to do any sort of measurements at that range. So what you need to do is sort of translate that limit back to a practical measurement distance, in this case, 10 meters. And so within the standards is that scaling factor in going from 300 meters to 10 meters is a frequency dependent thing, because near field, far field transitions are frequency dependent. And so you have anything from a 1/r to a 1/r cubed variation in that field. And the end result is sort of this red curve, frequency dependent curve. This is a plot of essentially magnetic field in dB versus frequency along the bottom axis. And right around the fundamental frequency, there's a bump up, that a chimney, as we call it, to allow for the fundamental. Now, this has been proposed to the FCC, and they're contemplating, it's still under study by them, to allow that chimney. In Europe, as I said, the situation is a little bit more complicated because of the debate ongoing about whether it should be treated as a ISM device versus treated as a full radio device, and that these devices have different limits there. I put them up here just to show you the difference between the FCC and then these two limits. If it's considered an ISM, you have to follow this golden line there. And if it's a radio device, you would have to meet the limit, okay, that purple line.
So, Morris, you will have 1 minute left. Oh, actually, we ran out of time, so you can wrap it up then.
Yeah, so this is last thing. So I wanted to leave you with the fact that a wireless power product is more than just the power transfer. It involves these other systems, but the technological challenges have been met, and it's ready for action. Thank you.
Thank you, Morris. Very interesting. So I got two questions in mind, but we are running out of time. So JC, can we actually forward this question to Morris, and then he maybe reply then, oh, is it not a hand? Okay. So I guess Al. So hey, thank you all for attending the keynote session. And thank you, Maurice, again for your excellent presentation. We see the technology is maturing. So because of the time limit, I'm handing it over to Al to start the next session. Al.
Thank you, Morris. So I think just about everyone is here. I think we're missing only one speaker, but so what we're going to do is I am going to control the 2-slide summaries, and each speaker, please on your slide, I will introduce you with the title of your slide, and then you have 2 minutes to explain your slide. So let me start now. Yuya Deguchi is from the University of Tokyo, and he's presenting sensorless metal object detection using transmission side voltage pulses in standby phase for dynamic wireless power transfer.
Hello, I'm Yuya Deguchi. Thanks for the introduction. Now I am going to tell you about the method of metal object detection for dynamic wireless power transfer, commonly called DWPT. In our method, by applying voltage pulses to the power transmission coil during the waiting time in DWPT, we can detect metal objects which generate heat in DWPT. Our research focused on metal object detection in DWPT. We wanted to know what are metal objects in danger in DWPT and what the suitable method is to detect it. The point here is that in DWPT, the power is supplied only when a vehicle arrives. Therefore, we expected that the metal doesn't generate much heat during a single charge and propose a detection method of applying a pulse voltage during the waiting time when no car was present. If there are a falling metal object, the current amplitude is reduced because the input impedance increases. We conducted a heating experiment simulating the DWPT to see what kind of metal object would generate heat, and a detection experiment to confirm the effectiveness of our method. As a result, our 20 kilowatt DWPT system needs to detect ferromagnetic materials larger than 50 millimeters square. When those metals entered on transmitter coil, the steady state current amplitude decreased by more than 20% from the reference value shown in blue as shown in key result. And we concluded that these were detectable. In conclusion, our method can detect dangerous falling metal objects in DWPT at a low cost without any additional sensors or circuit. Thank you for listening.
Thank you. The next speaker is going to speak about the study of the induced electric field system on inductive power transfer. And the speaker is, let's see. Please continue. I don't see an author speaker here.
Hello, can you people hear me?
Yeah, is this Zishan?
Yeah, okay. Okay, the study of induced electric field effect on the inductive power transfer. So in our method, we have reduced the induced electric field effect on the in the coils. So for that, we have to make we have to make a topology. So Where is the first? Hello, the first slide. Can we?
Okay.
Okay, yeah. So this is the basic structure, like a typical configuration IPT system. So here we have to make here we have a ground, so like a shielding plate, then we have a core, and after that is a coil. So like here in the distributed stray capacitance transmitter. So like in the coil, we have a stray capacitance between the coil and the core and the shield, and we have neglected the coil and the shielding plate stray capacitance. So like general we take like in the conventional compensation capacitors, and here we have made this one like in our method like a distributed compensation circuit. So the structure is that we have divided it in a different segments. Like here, the capacitor C, like the C, this has the same resonance capacitance like the C1, C2, and Cn. And we have made equivalent circuit model of this. So for the reductions of the induced electric field in our proposed topology. So that was the all reason. Slide 2. Yeah, so okay, so during the simulations, we see that the magnetic field, that were the SAMs, and the induced electric field, so that was decreasing. And when we come to the current density in the core, so look at the C, this segment 1, it was the same as the general which we are using in our general proposed topologies. But if you look in our method, so like the segment 1, segment 2, and segment 4, so we have decreased this induced electric field. And also like doing the, this is the practical structures, like look at this. If we see it here, okay, that the capacitance between here, here, and here, they are the same, the resonance capacitance of the capacitor. And if we come here, like the power losses, so in the first segment, we have a losses like 11.82 watt. And if we see in the segment 2, it decreases to 11.5, and segment 4, it decreases to 11.
Can you wrap up in 10 seconds?
Yeah. Okay. So like, and FEC to the leakage current. Okay. So the leakage current is also decreasing. So look at the segment 1, segment 2, and segment 4. So the leakage current between the segment 1 and the segment 2, this is decreasing on a huge amount. And here the power loss is also decreased in the huge amount. But if we go like from the segment 1, 2, 3, and 4, like 5.
Thank you. Thank you. Thank you. The next speaker is Reza Keralahi from Drexel University. Wireless series parallel capacitor charger for DC circuit breaker applications.
Professor, and hello everyone. Thank you so much.
Please continue.
Yeah, thank you so much. So this paper as a goal, define the goal, and this paper present a capacitor charger for active injection DC circuit breaker. So within the active injection circuit breaker, we have a capacitor that needs to be pre-charged, and this capacitor is used to generate a resonance current to oppose the main currents in the circuit breaker. So the objects, the application of our paper is designing a capacitor charger for DC circuit breaker. The design objectives is designing a capacitor charger with 3 main design objectives. The first one is fast charging time, or minimizing transient response time. The second one is minimizing the steady-state power losses, and the final design objective is obtaining high voltage isolations. So with respect to the methods, we applied series parallel topology as a capacitor charger in active injection circuit breaker. And we analyze the effects of the main parameter that affects the transient response time of the series parallel topology and helps to reduce the charging time in SP topology, because within the circuit breaker, reclosing process is really important and we need to reduce this time. And last, we propose a new burst switching mode to minimize the steady state power losses. Regarding the Q result, we studied 4 parameters that affect the transient response time of the charging series parallel charging converter. The first one is that increasing the coil's quality factors of the primary and the secondary coil helps to reduce the transient response time. Minimizing the injection capacitance or the load capacitance can help to reduce the charging time. And reducing the input to output voltage ratio considerably helps to reduce the transient response time and help to charge the load capacitance fast. Also, to achieve high efficiency, we reduce the input DC link voltage to reduce the steady state power losses, and also we implement the pre-pause burst switching modes based on the leakage current of the load capacitance and also based on the connected circuit breaker to the load capacitance. At the conclusion, wireless SP topology can naturally provide high voltage isolation in active injection DC circuit breaker. Also, wireless SP topology can obtain fast charging, fast capacitor charging during reclosing process of the circuit breaker. And also, steady state power losses can be reduced almost to 0 using the pre-pause burst switching mode. Thank you so much.
Thank you. The next speaker is Seokyeon Son, Foreign Object Detection of Wireless Power Transfer System using Sensor Coil from KAIST.
Hello, can you hear me?
Yes, we can. Thank you.
Yeah. Hello, I'm Seokyeon Son from the KAIST. I will start the presentation with the theme of foreign object detection of wireless power transfer system using sensor coil. The principle of WPT is to use the Faraday law, which, as shown in the figure, result in induced voltage when the magnetic flux from the transmitting coil pass through the receiving coil. However, if metal object exists between the transmitting coil and the receiving coil, it causes added current, which causes critical problems such as reduced efficiency. So simple metal object detection methods using small sensor coil is proposed. As you can see in the lower left picture, sensor coils are wound around the transmitting coil, so the mutual inductance between the transmitting coil and the sensor coil occurs, and when the metal object exists, the mutual inductance change. Simulation results show the location of metal object near the sensor coil. We have confirmed that the metal object exists where the mutual inductance difference is large. Experiments also confirm that the location of metal object can be found through mutual inductance difference. Next, let me tell you about the conclusion. We propose the methods of detecting metal object by winding small sensor coils on a transmitting coil. And we analyze metal object existence and position through simulation and verify the simulation results through the experiments. Thank you for listening to the presentation.
Thank you. The next speaker is Chungmin Lee, also from KAIST, EMI Reduction Method in Wireless Power Transfer with Increasing Efficiency Using Frequency Split Phenomena.
Can you hear me?
Yes, we can. Thank you.
Hello, everyone. Previously, there was a lot of research on reactive shielding method. Reactive shielding method can reduce the magnetic field, but the disadvantage exists that the efficiency is reduced. Therefore, the goal of research is reactive shielding method with increasing efficiency. Proposed shielding method use frequency split phenomena. If overcoupling occurs between the two coils, frequency splitting may occur and the resonance point is divided into 2 points. Therefore, it is possible to operate in the capacitive region at the fundamental frequency and operate in the inductive region at the third harmonic frequency. proposed method was verified by simulation and the experiment was conducted as follows. It was confirmed that the efficiency increased because the current of the same phase as the TX coil flows when shading coil system is applied. As a result of EMF experiment, it was confirmed that the shading coil operates in inductive region at the third harmonic frequency. Thus, it can be seen that shading coil cancels the magnetic field. Finally, we propose a reactive shading method using frequency split phenomena and verify this through simulation and experiments. Thank you for listening.
Thank you. The next speaker is Sung-Ho Woo, also from KAIST, EMI Reduction Method for Overcoupled WPT System using Series Non-Topology.
Can you hear me?
Yes, we can.
Yes. Yes, in the WPT system, when the air gap is small or the Q value is high, the frequency split phenomenon may occur. When the frequency split occurs, various problems such as reduction in power capacity or exaggeration of EMI may occur. So it is necessary to analyze EMF EMI when the frequency splitting occurs. The series non-topology does not have compensation capacitor at the receiver side, which is the difference from SS topology. As you can see lower left figure, the magnitude and phase of input impedance for SS topology and SN topology were compared. When using SN topology, the magnitude of input impedance for fundamental component decreases, which means mitigation of power capacity problem. In addition, the magnitude of input impedance for odd harmonic component decreases, which means mitigation of EMI problem. The experimental results show that the efficiency of SN topology is 81%, and it is a result of 1.21% decrease compared to the SS topology. And EMI decreases by 30 dB to the maximum. Finally, let me tell you about the conclusion. When overcoupling occurs in the WPT system, the various problems may occur. When using the SN topology, it can solve the problems of overcoupling WPT systems, such as reduction in power capacity, EMI, while minimizing reduction of efficiency. Thank you for listening to the presentation.
Thank you. The next speaker is Shin-Yu Ho, wireless power transfer of online monitoring equipment for high voltage transmission line based on double-sided LCC resonant network from Chongqing University in China.
Hello, everyone. I'm a PhD student at the Institute of Wireless Power Transfer Technology, Chongqing University. The subject of my talk is wireless power transfer of online monitoring equipment for high voltage transmission line based on double-sided LCC resonant network. What I'm going to present is still only in its early stage, but I really think that our findings so far are worth telling you. The whole system consists of magnetic energy high voltage, an AC/DC power converter, a DC/DC high voltage inverter, LCC resistor network, relay coils embedded in insulator, a high frequency AC/DC power converter, and the online monitoring equipment. This paper defines that the system operating frequency is omega. The transmission call resistance frequency is omega 1. The relay resistance frequency is omega 2, and the releasing call resistance frequency is omega 3. The parameters can be obtained from these parameters. Omega 0 is the design frequency, which is given where cross-coupling effects of magnetic resonant networks will cause the max output voltage to slightly shift away from the resonant frequency. So this paper proposed the following 3 working modes. And in mode A, omega 1 and omega 2 and omega 3, omega 0 are equal to each other, where omega 0 is a fixed value, which has been determined before the system design. For multi-relay WPT system, the optimal operating is often not omega 0. The offset of the operating frequency between the LCC resonant network as a transmitter and the receiver, which will cause the constant current conditions of the transmitting coil and the receiving coil to be destroyed. Therefore, this paper proposed the following two working modes. And in mode B, omega 2 and omega 0 are equal. Omega 1, omega 3, and omega are equal to each other. In mode B, regardless of setting of the operating omega, the LCC concentrator network as the transmitter and the receiver resonate normally. In mode C, omega 2, omega 3, omega 0, and omega are equal to each other. The difference from the omega B is that output power and the constant.
Continue. Thank you. Can you wrap it up in 1 or 2 sentences?
Yeah. And the constant voltage capability of the system are improved by changing resonant frequency omega 2 of the relay coils.
Thank you.
Oh, thank you.
The next speaker is Jonathan Dean. Jonathan, are you on here? Oh, here you are. Okay.
Yes. Hi.
Wonderful. Jonathan Dean, Tennessee Tech University, Center for Energy Systems Research.
Right. So basically our goal with this was to create a alternative or provide an alternative to some of the issues we saw with scalability for wireless power transfer methods that are currently available applied to wireless sensor networks. And so our solution is called QUIC, which is quasi-wireless capacitive power transfer, which is a unipolar resonant capacitive power transfer method that basically allows us to have a single contact or contactless power transfer when operating at the resonant frequency. And so to do this, it uses a quarter wave resonator. And so basically what we did here is we designed a 2 different sensor nodes with the same structure. And one of them is a capacitive wireless variant and another is a single contact variant. And you can see them in the bottom left. So we looked at kind of the packets using TCP and wanted to see if there was any noticeable Wi-Fi interference, which we did not see any noticeable Wi-Fi interference. And in addition, we wanted to measure the efficiency as kind of a preliminary result. And using a Class A amplifier, we were able to see an efficiency of 39.6% and our quick power transfer efficiency. So just the capacitive link is at 52.6%. And so, and we're still, continuing to improve that. So basically, we were able to show here that since it can be surface powered and we've done experiments in-house that basically allow us to show that it's not very alignment dependent. We see this as a potential scalable approach to powering multiple sensor nodes on a surface.
Thank you.
Thank you.
The next speaker is Javier Stillig from the University of Stuttgart. Modular WPT system for the supply of mobile industrial production equipment.
Yeah, great. Thank you, Al. Well, first, I would like to say I like your base cap. Maybe you can put it in a chat where you can buy it. It's great. I love it. So yeah, let me show what's my paper about. In this paper, we make a proposal for how to supply lightweight machines, small robots, transport vehicles wirelessly with electrical energy. So as you can see in the upper left corner, we bring the vision of the factory of the future step by step into reality. In the factory of the future, all production equipment can be moved freely on the shop floor in order to be reconfigured and optimized to the market demands. Well, to realize this production technology, this level of production technology, we developed the so-called intelligent floor, which is, among other things, equipped with the here presented WPT modules. These modules are designed to transfer power up to 3.7 kilowatts and with an air gap of 50 millimeters. So in our paper, we describe especially the supply of AGVs, where one module is limited to provide 100 watts for a constant feeding of small size batteries, onboard batteries. So we decided for our application, we decided to apply to a LCC compensation on primary and secondary side due to the WPT system current source behavior at the output. So especially during the dynamic charging operation, the wide variation of the coupling factor, which is between, in our case, between 0 and 0.45, then it's uncritical for the connected load or for the WPT system itself when you use a LCC compensation. So what we did is to simulate the K factor and to calculate analytically the values of primary and secondary LCC components. After that, we simulated the complete circuit with the help of SPICE. And to have a good knowledge about the system's behavior, when we set up a prototype, we wanted to set up a working prototype in a first approach. So performing the first experiments in the lab, we found out that the functionality of the dynamic charging is working very well. Further, the calculated output values could be achieved within a tolerance of minus 20%. So this is a great value, but I would say a sentence after that. Well, this result shows that the principal goal of powering machinery wirelessly could be achieved by using such modular and floor-based WPT module units. So, but today, the analytical calculations do not consider the soft magnetic core and the losses in the power electronics as well. Different state of misalignment of primary and secondary side precisely enough. To obtain better results, further research it's going on, and we actually carry this out. So thank you for attending to my presentation.
Thank you, Javier. The next speaker is our last paper for this session. It's Tim Krieger from TU Dortmund University in Germany, a 2 megahertz compact wireless power transfer system with voltage conversion from 400 volts to 48 volts.
Yeah, hello. Can you hear me?
Yes, I can.
Okay, thank you. To supply fast-moving actuators in modern industries like clean rooms or other industrial plants, we need wireless power transfer systems, which are really compact, and we want to transfer a power of 500 watt with a high power density of 25 watt per square centimeters. Also, we want to step down the input voltage of 400 volt, which is a typical DC grid voltage, to 48 volt, which is a typical onboard voltage. Our method is shown in the equivalent circuit, which is an all primary referred equivalent circuit of the transformer. With the transformer ratio, we supply the 400 volt to 48 volt conversion. And on the left side, we have an inverting half bridge with gallium nitride hems. The all primary referred equivalent circuit brings us the LLC topology with LR, LM, and the resonant capacitor. So we only have to compensate on the primary side. The LLC topology brings us the zero voltage switching possibility, and this allows high switching frequency for the high power density. And we only have to compensate on the primary side, which keeps the secondary side quite compact and simple. On the secondary side, we use a center tapped coil to use only 2 diodes for rectification. This secondary coil is included into the PCB, which keeps the receiving side quite compact. And with this system, we achieved a high power density with high switching frequency of 2 megahertz, and we transferred 500 watt with 91% efficiency from DC to DC. This shows the advantage of zero voltage switching possibility, and the use of GaN hems is quite well. This system is quite attractive for many industrial applications. Thank you for listening.
Thank you. I noticed I neglected to introduce myself. I'm Al Vestrus from the University of Michigan, one of the technical program chairs for this conference. We're going to go ahead and answer questions. The first question asks, I believe this question is for Jonathan Dean. What do you mean by quasi-wireless?
Okay, so by quasi-wireless, what we mean is that we have, it has the ability to be wireless or to be, so we refer to it as contactless since we generally are close to surface power. So it has a contact or contactless variant. So it is quasi-wireless in the sense that we could send it through a single conductor if we wanted and not have a return path, or it's a capacitive return path.
Okay, thank you. If you have any questions, you're in one of the attendees. On your Zoom screen, if you just press the Q&A, questions will show up over there, and we'll answer them. Right now, I'm going through each of the speakers to see if there are any individual questions.
Well, hey, Al. So there are actually 4 questions in the answered one. It's actually not answered. We can go through them, 3 of them actually for Morris. So we can probably take this opportunity since we don't see any more questions.
Okay, certainly. Mauro Feliziani asks, in the real world, does the size and material of the vehicle affect efficiency of the power transfer? Are there any problems with EMC immunity tests? And this is for Morris Kessler. And he responds, the underbody of the vehicle can have an impact depending on the material around the vehicle coil. Steel exposed to the magnetic field can heat, but a simple thin aluminum shield around the vehicle coil can eliminate that. EMC limits can be met with a well-designed system. Emissions at the fundamental frequency from the circular coil pair is generally not a concern. Okay. The next question is from Zichao Lo for Morris Kessler as well. What is the most likely scene for the commercial EV wireless charging being used first? Do we need to wait for the autonomous driving technology to be fully developed? The response is certainly no need to wait for autonomous technology. The first systems will be deployed in a home or residential environment, with public charger deployments following when more vehicles are equipped with wireless charging. Danilo DiCiccio asks, 300 kilowatt per hour in WPT is real now or future benchmark? If it's a future benchmark, how much maximum limit WPT will be right now? Systems have been built at 300 kilowatts, so that is real now. For light-duty vehicles, the standards currently go up to 11 kilowatts, and the first systems will be deployed up to this power level. Franklin Bartels asks, hi, Mr. Kessler. Talking of misalignment of the receiver coil with the transmitter coil, what is the impact on the rate of EV charging and what degree of misalignment is acceptable? Morris Kessler replies, the standards define a misalignment range of plus or minus 75 millimeters in the direction of travel and plus or minus 100 millimeters in the transverse direction. It is possible to transfer full power over this range of coil offsets. There's a new question for Zishan Shafiq. Which parameters of WPT system were taken as sources, that is input data of electric field and magnetic field in the simulation? Was it only primary current? Zishan. Okay, he's not responding now. Let's see.
Oh, he's on mute. Zishan, you're on mute. Oh, so all right, no response.
Don, how do you open up a question in Hoover? Oh, I see.
Yeah,
okay.
there's a Q&A and
I see
yeah.
the question. Okay.
Yes.
So for Changmin Lee, thanks for a good presentation. I have one question. Is it possible to apply the method on the receiver side? Changmin, would you like to reply?
Yes. We consider the RX coil shielding system. As a result, the frequency splitting phenomena of RX coil can also be used, but the EMF reduction effect is so smaller. Therefore, I think more analysis is needed.
Okay. Thank you. This is a question for Sang-Yun Son. How should the number and location of sensor coils be determined?
The location and number of sensor coils change depending on the size of the WPT system, since the number of turns in the sensor coil also affect the size of detection area. So it is necessary to optimize the location and number through simulation or experiment. Thank you.
Okay. So here's a question here for Sang-Yun as well, TS4-4. Thank you for the presentation. Questions. Was the mutual inductance increasing or decreasing when the FO was close, foreign object was close?
The mutual inductance has decreased, and so I checked the location through the mutual inductance difference.
Okay, and so you used metal materials, right, as your foreign object in general?
I used the Korean coin and also aluminum can.
Okay. And so here's a question. Did you have a receiver coil running while you were doing foreign object detection, or this was only when the transmitter and receiver were off?
There was only transmitting coil and sensor coil because before the transfer, we can detect foreign object.
So do you think the receiver coil will affect your ability to detect foreign objects?
Please say it again.
Do you think having a receiver coil will affect being able to detect foreign objects?
It can affect, but this system can detect foreign object as well.
Okay, thank you. There's 3 questions here for Sung Ho Woo. How do you decide the capacitance of the primary coil in the series non-topology?
The SS topology considered inductance of each side when calculating compensation capacitor, but when calculating compensation capacitor at TX side when using SN topology, TX and RX inductance and mutual inductance and load resistance should be considered. This is the difference from SS topology.
Okay. Is it possible to use an NS topology instead of a sort of a series non-topology, SN topology?
I think Muhammad asked what kind of application it can actually be applied to. First, it seems to be applicable to applications with small gaps such as mobile applications. And additionally, if Q is large, frequency splitting may occur even if K is not large. In the SS topology, which is a commonly used topology when the load resistance is small or the inductance is large, the frequency splitting phenomenon may occur because the Q value is large. I'm currently conducting research on the efficiency and EMI comparison of SS topology and SN topology according to Q value or K value change. Thanks for asking me question.
Thank you. Let's see here if there are any other questions here. Oh, here's another question in the chat box. Are there any searches for dynamic wireless charging? What efficiency? So this might be a question for Morris Kessler, actually, who's I don't believe is here anymore.
No, I'm still here.
Okay. Are there any searches for dynamic wireless charging? What problems are encountered in dynamic charging and efficiency?
There's certainly actually systems that have been trialed in the field for dynamic wireless charging. So it's certainly possible to do it with the same types of coils and things that you find in a static charging situation. Problems are just that, maintaining the alignment tolerance that you need as the vehicle is moving. You need some additional electronics on the secondary side to handle the sort of lumpiness of the power delivery. Efficiencies can be good, similar to what you can get with static charging.
So Morris, I actually have a question myself. So do you worry about metering the wireless power transfer? I ask this because, you're going to have different providers for the chargers, and you're also going to have different customers, and their own efficiencies might be different. So in a way, you kind of want to be able to really be able to discount sort of like, so where you measure. So you really sort of want to measure the energy going from one to the other. So is this something you guys are thinking about?
That's a great question. And there have been some groups considering updates to how to update the NIST standard for metering requirements to accommodate wireless charging. Typically, like for a conductive charger, the measurement's done at the inlet to the car. So the equivalent for a wireless charging system would be somewhere in between the ground coil and the vehicle coil. But obviously that's a difficult measurement there. So right now, things are being considered like, where on the ground side would you measure the power? Can you do something like take information from like what the coil currents are in order to determine sort of an appropriate metering for the power delivery? So good question. And there's no agreed upon solution yet.
Thank you. Okay, let me see if any of the final talks here have a question. So please ask questions if you're in the audience. Dr. Morris Kessler is still here, so if you
Yes.
have questions for him.
Okay, Al, this is Don.
Hi,
So actually, just I have a question for Morris. So you in your chart you mentioned the cost aspects, but you did not have a chance to elaborate. Can you actually elaborate a little bit more on the cost, especially relative to the so-called static charging station that's currently being deployed?
So yeah, certainly the cost targets are to be compatible with conductive charging. Ultimately, the system for a AC conductive charger, there's an onboard charger. Once wireless charging is more widely deployed, potentially you can eliminate that. So the vehicle component of the wireless charging system can be sort of a replacement for that. DC charging, most of that sits off board, and that can be a good augmentation for very high power charging for light duty vehicles. So you might see a combination of wireless charging for most charging use cases, which tend to occur overnight, and DC fast charging. But the cost point is to, try to reach parity with that ultimately.
Okay, thanks.
Okay.
Al, back to you.
Yes. So we have more time. So please ask questions. We have a group of really enthusiastic presenters here looking to talk about their work. So. Perhaps I can prompt one of my students to ask a question.
Just tell them it's a test. So to make sure
So were you actually listening? Okay. I don't quite see a fully formed question here. Anyone else want to ask a question? There's a concern about the electromagnetic compatibility, as in terms of spectrum. With I guess this might be a concern for many people. This is, I guess, for Dr. Kessler, about EMC from wireless power transfer affecting, let's say, communications and other types of the spectrum.
Well, that's something that we're looking at. We've actually done measurements as part of the SAE standard development of amateur radio communications and a system operating, and showed that there was minimal interference on normal operation there. So it's an ongoing topic of discussion in Europe. As the questioner is probably aware, and we're trying to make sure that limits that are set that don't cause interference with these existing radio services.
Thank you. Any other questions?
All clear. No more questions.
Wow. Everything was completely understood, every single bit of the paper.
That's good.
Well, I'd like to take the time to actually thank Dr. Kessler, actually, and Genshan actually thanked him as well for answering questions in this Q&A session, actually staying longer than you were supposed to. I very much appreciate your talk as well and your support. Thank you very much.
Thank you.
Thank you, Morris, and all the presenters too.
Thank you to all the presenters for you know, this whole event is difficult in that it's virtual, and I'm hoping to very soon be able to see all of you as well as everyone else here. I hope so, to actually have a live conference after all, and next year, looking forward to it as well.
Okay, next year, yeah, most likely.
Let's hope so. Thank you.
Yes. Okay.
Bye-bye.
Good. Bye-bye, everybody. Good day.
I think I will close the session. Thank you everyone for attending and asking questions and participating. Chris, would you like to say anything, or we're great? Okay.
No, I think I also appreciate everybody else, the keynote, and also everybody else participating in the conference today. Really appreciate it. And I hope everybody enjoyed it. Thank you, and I'll see you soon at another session. Bye-bye.
Thank you, everybody.
Bye-bye.
Thank you so much.
Thank you. Bye.
Thank you so much.